Yay! So, in my part one video of this thought experiment with regard to the weak and strong forces, the subatomic weak and strong forces discussion, I did the setup, again in part one of the video. And very quickly, we have a helium atom model here. It's not to scale. The electrons would need to be, this one would need to be 25,000 feet that way, which takes you all the way over to I-65 and Worthsville Road. And this electron would need to be 25,000 feet the other way. I'm a little off camera. The other way. Anyway, so let's understand that scale. So if this is the size of protons and neutrons, these electrons are off screen by far. Okay? So protons and neutrons are not that big, and electron clouds around atoms are not that big. As a matter of fact, they're so small that we can't see atoms with a microscope. This is 1 times 10 to the minus 10 meters. We don't have microscopes that let us look to the 10 to the 10 power. Are you following me? They don't exist. So we can't, a helium atom we can't even see. So we make models of it based on evidence. And we get this evidence when we have helium gas in a jar and we bombard it with electrons and we see shadows that form, and that allows us to get the diameter of a helium atom, okay? And the diameter of a proton, and there might be other things we've done to get the diameter of a proton, and the diameter of a helium atom nucleus, okay? But we get these things in various, we have evidence for estimating these diameters. You'll notice they only have one significant digit, these numbers. This one has 2 significant digits, but I decided to give this one 2 significant digits to differentiate between this one and this one. Maybe I should write down 2 times 10 to the minus 15 meters. But this was available in the, what would I call it? From the World Wide Web Library. I got this from the World Wide Web Library. I got that also and this also. Okay? So now, review. The mass of a proton and the mass of a neutron are the same, 1.67 times 10 to the minus 27 kilograms. The Newton's gravitational constant is 6.67 times 10 to the minus 11. Coulomb's electromagnetic force constant, K, is 8.99 times 10 to the 9th. And the elementary charge is 1.602 times 10 to the minus 19. So this elementary charge is negative on an electron and positive on a proton. Okay? And as I said, I want to answer some questions. The questions I'm trying to answer are, what is the force that the gravitational force for this proton to stay next to these 2 neutrons and this proton in a helium atom? What is the gravitational force? And we can figure that out. What is the, and I'm going to assume that that gravitational force here at the nucleus of the atom is a lot more than the gravitational force between this electron and this nucleus of the atom. Are you following me? We could figure that out, but I don't think I'm going to figure that out in this particular thought experiment. Okay? But there is a gravitational force between these masses. There's a mass of an electron we would need to know. I don't have it here. We would need to know the mass of the electron in order to calculate the gravitational force between an electron and a nuclei of an atom. But it's negligible compared to the electrostatic force, and we'll see that. We're going to see that by analyzing this, the gravitational force between the proton and the nucleus of the atom, and the electromagnetic force between these two positively charged particles. And then we're also going to look at the electromagnetic force for the electrons. The subatomic strong force is going to be greater than the electrostatic force of repulsion created by these two positively charged neutrons being next to each other, or in each other's vicinity. Okay? There's going to be electrostatic force because of this. All right? And that's going to be incredible. And of course, remembering that these electrons are not this close to the nucleus of the atom. They're so far away that distance squared right here makes this less, much, much, much less. Okay? So that's why they call it the weak force. And then the subatomic strong force that holds the nucleus of an atom together. Now, again, I'll just get started now. Okay. So I have to turn the camera for you to be able to see this board, and we'll come back to that diagram and that data on that other board. Okay? So, what is the gravitational force for that proton and that neutron? I'm actually going to redraw the diagram so that you can see what it is we're doing. Okay? So there is this, I'll use red. I'll stay with my color code. Red for protons, black for neutrons. All right. A few assumptions go into me creating an alpha particle that looks like this, okay? Or the helium nuclei that looks like this. One, the neutrons being present in the nuclei of the atom make it stable enough that it doesn't fly apart. These protons are positively charged, and they repel each other. So I'm assuming, and this is an assumption, that the alpha particle becomes flat and geometrically shaped like this in a flat plane. If I cut through the helium atom at a plane of symmetry, this is what it would look like. Where the positively charged protons are still together, but as far apart from each other because of the stabilizing neutrons. All right? So that's an assumption on my part. That allows me to do what I'm about to do, and you'll see why. So this guy, the diameter of this guy, we know is 1 times 10 to the minus 15 meters. Okay? And we know that the diameter of the whole thing is 1.6 times 10 to the minus 15 meters. Okay? So if you have two neutrons and a proton, and they're all three touching each other, where is the center of gravity of those three particles? Well, it's right here. Okay? The center of gravity of those three particles is right there. All right? And we know that this is the diameter of this, the average diameter of this particle, of this alpha particle, is 1.6. All right? 1.6 times 10 to the minus 15 meters. Okay? 1.6 times the diameter of a proton. All right? The average diameter of a alpha particle. And that makes sense. Good. I'm glad that makes sense. I'm glad they didn't say this is something like, 10 times 10 to the minus 15 meters. Because that wouldn't make sense. necessarily. Unless the neutrons and the protons weren't touching each other at the nucleus of the atom. But I've never seen a model, an atomic model, where the neutrons and the protons don't touch each other. And I think that's true because this is given in literature that 1.6 times 10 to the minus 15 meters is the diameter of a helium nuclei. Okay? So, now, what is the force of gravity? The force of gravity is equal to G times m1, m2 divided by the distance squared. Okay? So, the force of gravity holding this proton against these other three subatomic particles is equal to 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Right? Yes. I remembered that right. I have to check myself anymore. I'm known to make mental errors. Pray for me. Okay, so 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared is G. I'm plugged in for G. Okay, now I'm going to plug in for M1. I'm going to let my proton be the mass 1 in this formula. Okay, the proton mass is 1.67 times 10 to the minus 27 kilograms. I suspect when I'm writing that you can't see it, so I'll point it out. This says 1.67 times 10 to the minus 27 kilograms, and that is the mass of a proton. Okay? The mass of a proton. Now, M2 is the mass of one proton and 2 neutrons. Are you following that? This other mass is equal to this neutron plus that proton. And there's the center of gravity of these three subatomic particles. So here we go. We got 3 times 1.67 times 10 to the minus 27 kilograms. And I'm sorry, again I blocked that as I was writing it. So this is 3 times this 1.67 times 10 to the minus 27 kilograms. Okay? That's the other mass, mass 2. Okay? Now the distance between those center of gravities of those two masses. Okay? I'm going to take it as so here's the center of here's the center of mass of this proton, here's the center of mass of those 3 particles. And so that distance to me looks about like the diameter of a proton. Okay? Without including the electrons in this drawing is to scale. So I can say from here to here, no, it's probably a little more than 1. Let's see here. Bam, bam. It's just a little bit more. So I'm going to say the distance is 1.2 times 10 to the minus 15 meters. All right? So D is 1.2 times 10 to the minus 15 meters. All right? And I got that by looking at the distance from this center of mass and that center of mass. And knowing the diameter of that proton is 1 times 10 to the minus 15. Everybody follow that logic? So 1.2 times 10 to the minus 15 meters squared, D squared. All right, so now I have plugged in the force of gravity. I have plugged in, and I'm ready to grab my calculator. Okay, I'm going to get my calculator. On. Clear. All right, 6 6.67 times 1.67 times 3 times 1.67 divided by 1.2 equals 294 times 10 to the something. Now we're going to go back and we're going to get the 10 to the something figured out, okay? Clear. So that's 11. This is 27. This is 27. And that is, oh, I don't think I divided by 1.2 twice. This is squared. I got to go back. Got to do this one more time. So I'm going to start over. Sorry, everybody. Notice how this is a little bit complicated, but it's not impossible. Let's go with it. 6.67 times 1.67 times 3 times 1.67 divided by 1.2 divided by 1.2 equals 38.75. Boy, that's so much different that I am going to check that one more time. Okay? Clear. 6.67 times 1.67 times 3 times 1.67 divided by 1.2 divided by 1.2 equals 38.8. Okay. So this is 38.8, and now times 10 to the something. Let's figure that out again now. This is 11 plus 27 plus 27, okay, minus, so this is, we'll just do the numerator first. This is minus 65. That comes up to 10 to the minus 65 in the numerator. The denominator is 10 to the minus 30. Okay, I'm going to put a circle around it because this is a sub. We're doing some subcalcs. Okay, so this is 10 to the minus 30. So this is minus 65 minus a minus 30, or negative 35. Okay. 38.8 times 10 to the minus 35 newtons. This is in newtons because your meters squared go away and your kilograms squared go away. You're left with newtons. Okay? Everybody follow that logic and math? So that's one answer. We could move this decimal place over here to the left one, and that would make this become 10 to the minus 36, right? Moving that decimal place over here. Okay? And maybe that's too many significant digits. Maybe we should say this is 4 times 10 to the minus 36 newtons. Wait a minute, I moved it to the left. This should be minus 34. Okay, since I moved it to the left, I need to multiply it by, I need to divide this by, I need to multiply by another 10. Yeah, so I needed to add 1 to minus 35. And that becomes minus 34. I'm sorry if that's difficult, but I didn't mean to create confusion there. Okay, just want to do it right. So so the force of gravity that holds this proton at the nucleus of an atom is 4 times 10 to the minus 34 newtons. All right. Now, what is the electrostatic repulsion between these two protons? Is the next question we want to answer. Okay? So we'll do that up here in this area. Can you see this area? Yeah, you can. Okay, good. So F sub E. F sub E is equal to K Q1 Q2 divided by the distance squared. Okay? Everybody see where we're going? K is equal to 8.99 times 10 to the 9th. And that is Newton meter squared per Coulomb squared. Okay? That's 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Now Q1, well, it is the elementary charge of 1.602, positive 1.602 times 10 to the minus 19 coulombs. And the other charge, the other charged particle here is 1.602 times 10 to the minus 19 coulombs. The other charged particle here is also 1.602 times 10 to the minus 19 coulombs, right? Q1 and Q2 are the same. And this distance between them, from this center of charge to this center of charge, is more like, let's see, there's one diameter, two, it's probably about 2. 2 times 10 to the minus 15. Do you agree? This was 1.2, we said. Maybe it's only 1.8, right? Here's this. Let's go from here to here, and from here to there. Yeah. And we're going to say 2 times 10 to the minus 15. Okay? 2.0 times 10 to the minus 15 meters. And that's squared. Right? D squared, Q1, Q2, K, D squared. Okay? So we're figuring out what is on this proton, we know that this force is a force of repulsion. These two protons are pushing away from each other because of the electrostatic forces between them. So we could draw a force vector, I'll do that in brown, in this direction. F sub E is what we're calculating right now in newtons. We just figured out F sub G here, which is that's in the other direction. This is F sub G. Okay, and I happen to know already that F sub G is negligible compared to F sub electrostatic force in this direction on that proton. Okay? But this is a free body diagram for that proton. Okay? So let me grab my calculator again. I'm sorry if this takes so long. On, clear. All right, 8.99 times 1.602 times 1.602, okay, divided by 2 squared divided by 2 equals 5.76, 5.77, okay, sorry, that's brown. I'm going to use black for this. This equals 5.77 is where we'll start. Okay? Now, the multiples of 10, let's add those up. This is 9, that's minus 19, so this is minus 10 in total, and then minus 19 is minus 29, minus 29, okay? Up here, the multiples of 10 in the numerator, and right here, the multiples of 10 in the denominator are minus 30, okay? So minus 29 minus a minus 30 is 1. So this is 5.77 times 10. We could leave the 1 off, but we'll go ahead and put it there. Times 10 to the 1. And that is newtons again. So this is, this Coulomb squared goes away with these coulombs, and this meter squared cancels that meter squared, and now you have newtons remaining. F sub E is equal to 5.77 times 10 newtons, or 57 newtons, right? Or 50, let's just say it's 50, let's just say it's 60 newtons. One significant digit. It's approximately 60 newtons. Okay? I'm going to make that 6 better. Okay? So, in a helium atom, the electrostatic force pushing those protons apart is 60 newtons. The gravitational force holding that proton against the nucleus is 4 times 10 to the minus 34 newtons. Are you following me? This is why they talk about electrostatic forces being greater than gravitational forces. In this situation, that's true. But if I had a charge that was different than the Earth's neutral, if you will, or the Earth's ground voltage, if I had a charge, I think the gravity that holds me down on Earth would be greater than the electrostatic attraction between me and the Earth, because I don't think I could live with a charge that would be great enough to overpower the massiveness of the Earth in these two different formulas. So you might find out that I would be dead if this force was greater than that force. So it depends on the situation, is my point. People talk about electrostatic force being greater than gravitational force, but that is situational, okay? Things with the same mass that would always be true. No, it wouldn't always be true. The force of gravity that, for instance, holds the Earth in orbit around the sun, that's an incredible force. It would be hard to overcome that with electromagnetic force. Take a lot of charge. Just so we know. I mean, I'm just trying to help us all understand what we mean when we say the electrostatic force is greater than the gravitational force. Okay? It depends on these other variables as well, and the situation. Okay. So look at how much smaller the force of gravity is to the electromagnetic force. Are you following me? This is incredible, the difference between these forces. Gravity has nothing to do with the nucleus of an atom holding itself together. That's the conclusion. The conclusion is gravity has nothing to do with holding, negligible. It's so negligible, you can say scientifically it has nothing to do with what holds the nucleus of an atom together. And that's why we know that the subatomic strong force is vastly different than the force of gravity. It's not the same force. Orders of magnitude in difference, okay? The difference of the forces, all right? So, that's one conclusion we've been able to draw looking at the geometry of this alpha particle. Now, let's look at the subatomic weak force, okay? Is it okay if I erase this? So this is an examination of the subatomic strong force. I think I'll save this information. This F sub E is 60 newtons, and this F sub G is 4 times 10 to the minus 34 newtons. Okay? I'll save that information right there. Now, let's bring into play the electrons. This gets a little more complicated. I'm going to erase this, and we'll start over. Okay. Now let's bring in the electrons. Now let's remember these electrons are way far away. Let's not think for a minute that this diagram is to scale. These electrons are way far away if my scale is this. If this is the size of a proton, then these electrons are these are a little bit smaller than my original diagram, because those electrons are way far away, and I'll just leave it at that. Don't forget that. Now, what is the force? And we've shown that the force of gravity is much, much, much less than the force of electrostatic force. So we're not going to figure out what is the force of gravity between this electron and this nucleus of the atom. It is so much smaller than this, because the distance between the electron and this mass, the mass of the electron and this mass, the distance is enormous in comparison. The gravitational force here, this would become I don't know what the number out front of the scientific notation here would become, but this 10 would become something like 10 to the minus 40 or 50, even way smaller, the gravitational force between this electron and this mass. Okay? Everybody follow that? That's because the force of gravity is equal to G times m1 times m2 divided by d squared. All right? Now m2, let's say, is this, and m1 is the mass of an electron. The mass of an electron is negligible compared to the mass of this. Okay? Remember when we were figuring out the gravity here, we were using the mass of the proton and the mass of the three other subatomic particles. Here's a mass of, well, the mass of an electron is an order of magnitude of 10 to the 5th less than the mass of a proton. And this would only be 1.25 of that other mass. So this numerator becomes 10 to the 5th smaller, and this diameter that we're dividing by becomes 50,000 larger. So, and that's squared. And we're dividing by something that's 50,000 larger squared. And so this F sub G between these two things is so small that it's not worth calculating. I hope you understand that. Okay? I'm not going to worry about calculating F sub G between an electron and the nuclei of an atom. It is very small. Okay? It makes this look huge. And this is ridiculously small. Okay? Now, the electrostatic force. What force is required to keep this electron out in orbit around the nucleus of this atom? Okay? So this is the F net. We're going to figure out F net, and that is going to be the subatomic. I'm sorry, not F net. This is the F net is 0. I think we want to say. Okay. So this force arrow that I'm drawing here, F sub E. Okay. We don't need to worry about this. That's 0. F sub E in this direction, not E, not F sub E, I'm sorry. This is this is the subatomic weak force, all right? So I'm going to say this is the subatomic weak force, SWF, okay? And now, what is the attraction, the electrostatic attraction between this nuclei and that electron? So here is F sub E. And we know that F net on that particle is equal to 0, which is equal to F sub E minus F sub SWF, all right? If F sub SWF were greater than F sub E, then this electron would move away from the nucleus of the atom. If F sub E were greater than F sub SWF, then the electron would move closer to the nucleus of the atom. It would start to accelerate. Do you understand that? F net is equal to 0, or the electron will accelerate toward the nucleus of the atom or away from the nucleus of the atom, as how we're handling this particular calculation. All right, so F sub E on this electron has two contributors. It has these two protons pulling on it, this F sub E, as well as, so this F sub E is equal to a couple of vectors. There's these two protons pulling on it, okay? And there's this electron pushing it away at any given moment. These two charges. That's how we're going to calculate F sub E total, okay? We're gonna look at the force of attraction between the nucleus and this electron, and we're going to look at the force of repulsion between these two electrons that are always opposite each other. For this thought experiment, I'm going to imagine that that's true, that the electrons are always opposite each other. And it makes sense that they typically are. If you'll remember, there's one more little detail you can remember about this from your chemistry class. If this electron has a rotation of this, then this electron has a rotation of this. Are you following me? So their spin is opposite. They talk about their spin being opposite in the s orbital, and I believe it's fair to assume that the probability of finding those two electrons opposite each other is great, very great, okay? Because they're in the same s orbital, spinning oppositely and flying around. This is a sphere, okay? But remember, this sphere wouldn't be on this whiteboard. It would be way far away on either side of this whiteboard. Don't forget that. Now, so these guys are, because they're negatively charged, I think it's a good assumption to say that they're opposite each other in orbit around the nuclei of the atom a lot of the time, okay? So that is the scenario that I am going to use to figure out F sub E, okay? And I know that there's a force of repulsion for these electrons, and I know that there's a force of attraction between this electron and this nuclei. So let's figure that out real quick, okay? So we know that F sub E is equal to the F of the F of the nuclei electron minus F of the electron. Okay, so we've got to do this, we've got to use Coulomb's law twice to figure out that F sub E. And then we're going to use this formula right here, the fact that F net has to be 0. We're going to use this formula to talk about what is the subatomic weak force. Okay? So, F sub E, we'll do the, let's do the electron, what's that called? Repulsion. This is the electron repulsion. All right? F sub E is equal to K Q1 Q2 divided by the distance squared. All right? Well, K is equal to, it's a constant that Coulomb figured out, 8.99 times 10 to the 9th. Actually, Coulomb gets credit for it because he wrote the paper. Anyway, history says that. Right? Now, what is the charge on an electron? What's Q1? Well, a charge on an electron is 1.602 times 10 to the minus 19 coulombs. That's the elementary charge. You've seen that in our previous, when we were figuring out what the repulsive force here is between those two protons, okay? So this is 8.99 times 10 to the 9th. This is 1.602 times 10 to the minus 19. This is negative. They're equal. 1.602 times 10 to the minus 19 coulombs. All right. We don't need that negative sign because we know that we know the direction of this force. The direction of this force is to the right. We're doing a calc on this electron, and we know the direction of this force is to the right that we're calculating right now. Okay. Now the distance between these two electrons is, if you remember from our previous discussion, right here, 1 times 10 to the minus 10. Okay? So the distance here is 1 times 10 to the minus 10 meters. That's a pretty small distance. Okay? Now, let's do it. So F sub E for the electron repulsion is clear. I think we'll find that this is not negligible, but it's certainly less than the attractive force between this guy and this guy, because the distance is half the distance between these two. The distance is half, but the charge is twice. Each charge, you know what I mean? So this is good. So the positive charge attracting this electron is 2 times the elemental charge. Are you following me? So there will be this won't be the difference between this electron repulsion and the electron attraction will not be negligible. That's why we're figuring it out. Okay? So here we go. Clear. Now I'm back to the form of the task at hand. Clear. 8.99 times 1.602 times 1.602 divided by 1 equals 23 times, this is positive 9, that's minus 9 minus 19 is minus 10, minus 19 is minus 29, and this is positive, oh, this should be squared. So positive 20, I'm sorry, I got to minus 29. Now minus a minus 20 is minus 9. 23 times 10 to the minus 9 newtons. Okay? Now, remember the force between these two protons, the electrostatic force between these two protons is 60 newtons. The force between these two electrons is 23 times 10 to the minus 9 newtons, which is much, much less, and it's much, much less because this is not minus 15. Are you following it? This is not minus 15. This is minus 10. Are you following me? So you go from times 10 to the 6 times 10 to the 1 to 23 times 10 to the minus 9. Okay, are you following that? Everybody follow that. So because the distances are massive. This distance is very small compared to this distance. The distances are massive in comparison, and so the force of repulsion between those two electrons is much, 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 much less than the force of repulsion between these two protons. All right? Now, what is the force of attraction? This is the nuclei / electron attraction. This is what we're going to do next. That's right here. That's shown right here. That's this guy right here. We just figured out what this guy is. Now we're going to figure out what that guy is. The force of attraction. Electrostatic attraction. All right. So we know, again, F sub E is equal to K Q1 Q2 divided by the distance squared. Okay? All right, so that's equal to, again, we're going to write it all out again because this is good practice. 8.99 times 10 to the 9th Newton meter squared per Coulomb squared times, well, the charge here is 1.602 times 10 to the minus 19 coulombs. And the charge here now is 2. 2 times 1.602 times 10 to the minus 19 coulombs. The charge on a proton and the electron are opposite, but they're the same magnitude. Okay? And there's 2 protons. And there's 1 electron. So the charge is, this is Q1 and this is Q2. And now the distance between those, the nuclei and that electron, well, it's half. It is 0.5 times 10 to the minus 10 squared. It's the radius. Okay? So we're just taking the radius of this guy. 0.5 times 10 to the minus 10 squared. You ready? Clear. 8.99 times 1.602 times 2 times 1.602 divided by 0.5 divided by 0.5 equals, this is 185 times 10 to the what? 9 minus 19 is minus 10, minus 19 is minus 29, minus a minus 20 is minus 9 newtons. Okay? So you see how these two, this is not negligible from that. So the force of attraction, the ultimate force of attraction for this electron towards the nuclei of this atom is actually, so the F sub E total, right, this is F sub E total, is, that's the nuclei / electron, this is the electron / electron, is 185 times 10 to the minus 9 newtons minus 23 times 10 to the minus 9 newtons. All right, this is the F sub E total. All right, so what's 185 minus 23? I can't do that in my head yet. 162. Not quite negligible. I'm going to round that to 2 significant digits. So that's 160 times 10 to the minus 9 newtons. Okay? And it's because of the distances involved, that's why this is called the subatomic weak force. It is orders of magnitude different than the subatomic strong force. Okay? I'm sorry, let's take this to let's take this to 16 so you can understand how many orders of magnitude it is. If we move the decimal place to here, then this becomes 10 to the minus 10. All right? So it is 10 orders of magnitude less in a helium atom. Okay? All right. So we figured that out. Now, let's talk about some other scenarios. Looking at the periodic table, I'm going to turn the camera 90 degrees so you can see the periodic table. I'm going to walk over there to it. Sorry about those white dots. Let's see if we can fix that. There we go. That's better. All right. Looks like I got 2 spotlights over here on the wall, and that's just what that is that's these light fixtures up here reflecting off the wall. This is pretty hard. You can't really hardly see this. From this distance and my computer, I feel like you can't hardly see it. But let's talk about uranium, okay? Uranium has an atomic number of 92. And of course you remember from your chemistry discussions that the atomic number of 92 of uranium means that there's 92 protons, okay? So here we have 2 protons in our helium atom. We have 2 protons. Now imagine 92 protons, okay? So what would you have to do? Or what would be the force? The force of repulsion for a proton being in the nucleus of that atom, okay? There would be, instead of 1 other proton at the nucleus of the atom, there would be 91 other protons at the nucleus of that atom. And the distance between that proton and the center of charge of all those other protons would be somewhat different, okay? It might be that the nuclei diameter of 1.6 times 10 to the minus 15 is maybe more like 20 times 10 to the minus 15, okay? But it's still going to be in the ballpark. But the charge is going to be huge, 91 times more. The charge on the other protons is 91 times more. So when we calculate the force of this proton moving away from the other proton in a helium atom, we get 60 newtons. But what's 60 times, let's say it's 75. 60 times 75 newtons is quite a few newtons, okay? So I want you to understand that what we've calculated here, while we're using electromagnetic formula, Coulomb's law, at the nucleus of an atom, what we're showing here is this is the least strong subatomic force. Okay? The subatomic force for larger subatomic strong force for larger atoms is enormous compared to the subatomic strong force for a helium atom. Now, maybe we shouldn't multiply by 75 because maybe we're talking about a proton in the middle of the uranium atom, and so all the other protons are pushing that proton to sit still in the middle of the nuclei of a uranium atom, right? So the geometry, I just want you to think about the subatomic strong force and how strong it is. And as you change the geometry of the atom and include more protons and more neutrons in the geometry of the atom, I want you to understand that the strong force tends to increase for protons near the surface of the nuclei of the atom. Okay? Fair enough? And so what causes those strong forces? Right? Well, they've got some theories out there in physics. They use quantum physics to talk about the mathematics of the nuclei of the atom. They talk about waves. When I say quantum physics, they take everything back down to a wave. And they actually admit that they do not understand the difference between the wave way of thinking about particles and the actual particles, the reality of the particles. They can't understand the difference between the waveform of the calculations that they're doing in modern physics and the reality of, so there's this, I'm not going to use the word imaginary, let's use the word wave. There's the wave way of thinking about nature, and then there's the reality of nature. And they do not know how to work through the barrier between talking about things mathematically in waves and talking about things in reality. Okay? That's something that modern physics admits. All right? So I just want you to know the four field forces that we recognize today in modern physics are gravity, electromagnetic force, we have Newton's law of gravitation, and we have Coulomb's law for electromagnetic force, and you saw me use those laws to figure out what the forces are for subatomic particles working on each other. Okay? Now, there's two, gravity and electromagnetic force, and then there's the subatomic strong force, which is the force that holds the nuclei of atoms together. And then there's the subatomic weak force. And you saw us calculate those. And you see the difference, orders 10 to the 10th order of magnitude difference between the strong force and the weak force when talking about a helium atom. All right? It's different when you talk about different atoms. Okay? And I want you to constructively understand that. Don't think that what we've done here is exhaustive at all. I mean, it's not. They have figured out, they call it quantum mechanics. They have figured out why the electron clouds work the way they work. They have mathematical formulary to talk about the electron cloud and electrons moving into higher energy states and then falling back down to lower energy states, and a photon of light coming off of that particular electron, the energy corresponding to the higher energy state minus the lower energy state, becomes a photon of light. And some of that is in the visible spectrum. And so that's why you can, when you're heating up different atoms, you can see those those bands of light. When you hold copper in a flame and you heat it up, so the electrons getting excited, vibrating more, jumping out to an outer energy, quantized energy state, falling back in. That difference in energy levels sends out a photon of light corresponding to a particular color in visible spectrum. Some of the electrons fall back and it's outside the visible spectrum, and we can't see those color bands on. I suspect copper makes several different colors, several different electromagnetic waves, and only some of them we can see. Okay? Are you following me there? So I want you to understand the atom and how it works. Okay? We're able to cause fission in uranium-235 when you bombard that element atom with a neutron. Bam! It turns into two different elements in a flash. Okay? And there's a lot of energy given off when an atom does that. And then when you have a concentration of U-235 atoms and 3 neutrons are given off from that fission, and those 3 neutrons go and hit other atoms. Bam! Those atoms go and hit other atoms. Bam! It's a chain reaction when the concentration of U-235 atoms is high enough in a chunk of uranium. And you can make a fission bomb. And you've seen that in Hiroshima and Nagasaki. Okay? And then there's fusion, nuclear fusion. This is what's happening at our sun, nuclear fusion. Hydrogen atoms have an isotope with a proton and a neutron, atomic number of 1, but instead of having only 1 proton at the nucleus of the atom, they'll also have a proton and a neutron. That's called heavy hydrogen, okay? Or isotope of 2, 8 hydrogen with an isotope of